So first announcement for the for Wednesday, we will still have a class because we discussed with the other two professors. We decide to this time we try to schedule things a little bit different because we I can't give the lecture on November 19th, basically next Friday. So we will cancel the next Friday's class. So we will still have lecture for this week. All right. So, but we don't have lecture for next Friday. And then I can't give lecture for December 6th, but I will try to. That is probably the last week. So I will try to see how to arrange things, either to move to stop the class one day late or something, or I give lecture maybe at night or something. Yeah. So yes. Yes. Yeah.
We plan to have lecture the weekend of next week for the weekend.
Yes, yes, yes. So great. So first, I think that I did mostly I don't know, question driven, or I tried to talk from my head for the last class because I can't have my laptop up. But I did some kind of review. So I reserve another few minutes if you have some questions about the exam or any topic you want me to briefly cover. So yes. 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 Sorry? Yes. Oh, okay. The ridge regression, that topic. Okay. So what you want me just try to explain this a little bit, or? There's a question on the yeah, right. Okay, just give me one second. Okay, so I scheduled a separate room for the DRC exam section. So this TA we're going to will be there. Yeah. So okay, so that question is trying to say when you adjust lambda, what the change for the training and testing? Okay, so there's the reason we want to have a lambda there is because there's a overfitting problem. So if you have lambda super small, it's not always, but a lot of time you will end up with overfitting. Overfitting, the indication of overfitting is your training accuracy is very high, your test accuracy is very bad. That is a clear indication about overfitting. So then you will try to increase your lambda. So once you increase lambda, you want to limit your weight. So this is kind of like to give you less budget for you to distribute among all your weights. So then this will decrease your overfitting. So at a certain point, you achieve the perfect lambda, which is like just right, not much overfitting, not much underfitting. So you will expect you decrease your training accuracy a little bit, but your test accuracy improve. All right. But then if you keep increasing your lambda, then you are suffer from underfitting because you are, you do not give sufficient budget at all to use in your model. Then you expect to, your testing accuracy would supposed to decrease. At the end of the day, if you have a really large lambda, think about that. If you have really large lambda, then basically you have everything set to 0. So then you will saturate, you will kind of stay at some kind of bad performance. Yeah, that is briefly the picture. I hope that answers your question. Yes. I forgot. This is last year. Last year, it's okay. I forgot. Just re-describe this again. I forgot that question. Oh yeah, yeah. Please. Oh. So this is this last year one? Yeah, so this is probably is trying to see if you without the regularization, probably you will get higher weights. Yeah, because you can't get much small, even smaller, because you need an extra constraint to push down. Yeah. So if you see some weights even larger, that is less likely. Okay. Yep. Okay, great. So any other questions? But I also have I think I also have the office hour, but also feel free to send the emails. Okay. Also for people who have DIC accommodation, if you, I'm sure you're supposed to already, somebody, I think that the Laura who just arrived, she's supposed already approaching you. If you haven't, then you should send an email to me. All right. Okay. So otherwise, I will continue with the clustering. Okay. The clustering is if you talk things in terms of supervised learning versus unsupervised learning, so clustering in that sense is another super important topic, because for certain people, unsupervised learning is almost some kind of clustering to a certain extent, but that is, of course, is not always true. But you can think a lot of time when we talk about unsupervised learning, we will use certain type of clustering mindset. Okay. I think I give a very brief introduction to why unsupervised learning is important, but because I didn't record, I suppose quite some people who rely on my online lecture. So I just repeat a little bit more. So for supervised learning, we assume we have ground truth. So somebody already annotate, or you already know what exactly each data points, the ground truth correspond to each data point. But a lot of time we do not have labels, or that is because either because maybe it's very, very expensive to acquire those ground truths for those observations. And or a lot of times it's a lot of work, very tedious work to annotate your data. Yeah, for example, I give an example during last classes. for example, a lot of medical images, it's very expensive to acquire ground truth because it's very powerful. You see let's say an X-ray, you say, oh, this patient has some problem, right? If we know that ground truth, then that is super useful. But a lot of time you require a trained expert to see that. So people with that expertise usually do not be freely available to annotate a large amount of data. So you end up with a lot of data, but not many annotation. Okay. So of course, there's many other scenarios, especially, for example, for the field I work, computer vision, you can switch on a camera, you can record every second, right? But if you ask people to annotate things inside, that is a lot of work. So this is not necessarily super costly, but it's super tedious. Yeah. So anyway, we may end up with a lot of unannotated data. What to do? We still can tell very useful information from there. So one of the very popular strategy is to do clustering. Clustering is to say, I do not need any label, I do not need any ground truth, I just have a bunch of data. But then I try to see how data can be grouped inside there. Okay, for example, a very trivial example, I give you some cat image, some dog image. I don't tell you which one a cat, which one a dog, you just self-group them. Then you will find out probably one cluster probably will contain majority cats, one cluster majority contain dogs. All right. So then you already naturally have two groups. Then probably you can just take a quick look. Hey, say this is cat group, this is dog group. So all data already clustered. Okay. So this is a very rough picture about unsupervised learning. For unsupervised learning, for clustering, we usually, at least in this class, we were talking about one is a centroid-based clustering, which is to assume each cluster we will try to, based on some centroid, we will try to discover some optimal or some good choice of centroid. Then we just try to see assign members to each centroid based on the distance. So basically each guy will go to its nearest centroid. Another one is distribution based. We will assume there are several distributions inside the data. We will try to say which distribution do we come from? Then using that to try to group data. Okay. So based on that, we have many different ways, like hierarchical, centroid-based, distribution-based, density-based. As another example I give is for example, one of my research topics is we do subspace clustering. Those things, the difference here is usually you assume there's some prior assumption about your data. For example, the subspace based clustering is if we assume your data have subspace inside, that means in a 2D plane, your data lying on a line, 3D plane lying, you're lying on a plane, or high dimensional, you're lying on a hyperplane. If you assume especially in computer vision, we have a lot of those data, they are kind of have a very nice subspace structure. As I mentioned, one example, for example, human face. If you see especially the frontal human face, they are very naturally the same person's same person's face under different lighting condition that form a perfect 9-dimensional subspace. So this is very surprising result. Yeah, but that is very helpful. So that means that if I have a lot of human face images, I can very naturally to assume I will class them by fitting them to the nearest plane. So with those, of course, if you do not assume them, then those data can be very difficult to cluster, because just think about the image, the ambient space, which is we call it for each image, you have so many pixels, you have a huge dimension, right? So it's difficult to cluster them. So those things are the background about first you need to pick what is the right feature you want to cluster, and do you have any prior understanding, distribution based, central based, then you make the right decision. Then another thing is how many clusters do you have? Okay, so this is actually the most difficult question to answer, and we I can say we do not know how to answer. We will give you one solution, one method to try out to say, try to answer this, but in general, it's very difficult. You have to, this is like a hyperparameter. You have to try. Sometimes I have to try a couple of times. Certain times it's a kind of obvious. You say, based on your understanding, there's 2 clusters, 3 clusters, but a lot of time it's not obvious how many clusters inside your data. Okay. Anyway, we have a, we are going to present 2 methods. One is k-means, one is called Gaussian mixture model. K-means is a centroid based method, no model required. We just try to find simple structure, let's say, points that close together. We will try to group them into one cluster. And Gaussian mixture model is another slightly more sophisticated. It's a model based. It tries to assume you have some, your model can be modeled by the composition of several Gaussian distribution. Okay. And yeah, it's slightly, you have a slightly more complex model. So both, yes, questions. Yeah, yes, usually when you do, later you will find, no matter which method you try to do, you need to provide the number cluster as a input variable. You need to specify, hey, there's 3 clusters, please find 3 clusters there. Yeah. We will tell you one of the able approach to figure out, but it's usually it's not obvious. Even that method not necessarily work. Yeah. We will talk about that. So both of these 2 methods, the k-means and this GMM Gaussian mixture model, they all have very similar operating philosophy. So you will try to start with kind of initial assumption. You assume, hey, maybe the membership looks like this. Then you based on that initial assumption, then you will try to do a little bit of adjusting, reassignment to make things a little bit better. Then you go back to say, hey, if current looks like this, does this membership need to be adjusted a little bit further? And you just iterate. You will see what does that mean. Yeah. So basically, you guess first, then you improve it. Then you re-guess it, then re-improve it. Okay. So let's see about k-means cluster. So assume we have a data set of n points, and x1, x2 until xn. So the xj is a feature vector representation of a particular observation. Okay. So with k-means, we will try to divide this data set into k subset. Okay, S1, S2, and Sk. And each cluster is defined by a centroid, U. And the U is the mean of all the data points in a particular cluster. Okay, so as we can, if we define this formally, we will try to assign each x to a cluster to satisfy this objective function at the bottom. Okay. Guess I lose my pen, so I use this to indicate. So this is a objective function we want to satisfy. As you can see, what we try to do is the mu. We have here we have k number of cluster, and the mu I is the ith cluster, cluster's centroid. So we want to minimize this. What does that mean? We want to assign. First we want to assign each of the x to its minimal to its nearest centroid, and also the centroid also need to be chosen in such a way the whole things will be minimized. All right. So this is actually a little bit of chicken egg problem. So because we need to the mu I is really decide on the SI, and SI depends on the mu I. Okay, because unless you decide your SI, you don't know how to compute the mu I, right? The mu I is the average of all your data. All right, but then without the mu I, you also can't really assign people to the right cluster. So you see the this loop here. Okay. So how to solve this problem? Then we come out with a k-means problem. So we will start with a random choice. You just say, if I know there's two clusters there, okay, I just try to pick 2 points. I say, hey, these two guys will be the centroid. So here we have this red and this green dot. They are two centroid. And then based on that, we will try to minimize the objective function we have, right? We will try to assign, by assuming these two centroid are the right one, we will try to assign points to the respective clusters, right? So we will end up with those red guy turns out more close to the red, and the rest or the green guy more close to the green centroid. So now, no matter how, we have a assignment scheme, right? So now what you can do is you can recompute your centroid. Do you agree? Because other green one is based on the assumption of your current green centroid, but that is probably not necessarily the optimal. So what we do is we use the current membership assignment, recompute your new centroid. So take an average of each color points, then you will see we move a little bit of those centroid now. So as you can see, we have a new centroid for red, a new centroid for green. Then we try to reassign by taking the new centroid. Looks like things improve a little bit, right? Now, if we are not happy, we will recompute our new centroid. As you can see, then we will reassign. And so we just repeat this. And yes, question. Sorry? You mean these two become one? Oh yeah. Of course, you need to you need to decide 2 points, right? You can't using one centroid. Yeah. The random choice, you have to make sure this is 2 different points. Yes. Right. First of all, it's possible you will not get a very good result because this is a randomized. So it's possible, but to have them to become the same points, usually we are not. I don't know how to, is there any proof to show it won't converge to the same points, but usually it won't, but still it's possible you will end up with 2 very weak centroid to get a bad clustering. That is possible, yeah. So not necessary, but usually how to pick the initial random points. I believe there's also method to do that, but we will not cover those. But in general, if you just randomly try it a few times, usually you will end up with some very good solutions. So this is k-means is a pretty nice and stable, but you do have some small chance to end up with a very bad solution. So you need to run that one more time. Yeah. So usually you will run this several times and pick what is the best. Yeah. But the good thing is if in my understanding, if we pick the Euclidean distance as your matrix, so basically you measure who is the nearest to you by using the Euclidean distance. This method should converge. At least they should. At the end, they should converge to a solution. Okay. So here is how we implement k-means from the sklearn. We will have a cluster. So first of all, you import your sklearn cluster, then you can call k-means. As you can see, you will tell I think that we will go into more details. We will have some short Jupyter notebook demo about talking about this. So basically, you will like this is familiar. Like now we know you create an object and then you start to call the class functions, right? So I hope this is a start to give you more meaning after you see these object and classes. We will give more examples about this k-means example. Okay. So now we will talk about how to choose k. Again, as I mentioned, this is a difficult question. A lot of time, this is probably the most difficult question to answer. How many k at the first place? Okay. There's more method, but here this is one of the very interesting method to say, can we just try with different k, with the intuition that if you have very small k, a lot of people will not get the right assignment, right? Because you just think if I have 5 clusters, these 5 clusters, if they are separate where, if I only pick 2k, then a lot of guys will have to travel a lot to match you, right? Because they don't belong, they don't stay in your neighborhood. So in that case, this is the distance, the sum of the measured distance. Remember, we have an objective function there at the beginning, right? Remember the objective function, I say chicken egg optimization problem, we count, but we can measure that. Once you decide a centroid, once you decide a cluster, you can compute what is the distance there. So if you have a too small k, you will end up with a very large distance. Once you increase your k, that total distance will decrease. But if you supply too much k, basically unnecessary make a large k, then the improvement will be reduced, will be minimal, right? Because since everybody already finds its correct centroid, then you say, I want to add another centroid. That more likely just make a good cluster into subcluster, right? That does not improve your overall distance reduce much. So which is reason, once you find just the right k, you're supposed to see elbow here. Just like an elbow is like you decrease very fast, then suddenly you decrease very slow. You can see this, basically the gradient there will change a lot. Okay, so then usually this kind of elbow point will give you some a very good indication or rough indication, very good rough indication about what k to choose. All right, does this make sense? Okay, obviously this is not it won't solve the problem. A lot of time you will see a very weak knee point in when you are facing real world problems. So in theory, this is a very nice strategy. So it's better than nothing. Yeah. So you can try to see what roughly what the k will be state, but it's hard to very accurate to get a number there. All right, for example, here we was trying to say, hey, k equal to 5 is probably a very good number. Any questions about k-means? So it's a very simple, but it's very powerful. And this methodology here is super important. All right, any questions? Otherwise, I will move to the Gaussian mixture model, which is another super, how say, very beautiful, another very beautiful method. And also we will introduce here EM algorithm, which is again is super important. EM thinking things in terms of EM way. Yeah. So here a Gaussian mixture model, basically with k components, or you can think about clusters, is a probability distribution that is a weighted sum of k Gaussians. So this is a distribution. If you have a data fitting into a distribution, then instead of you are trying to fitting into one Gaussian, you try to think this distribution is a mixture of multiple things. Then this becomes very powerful because you just think about this red curve here. This red curve is a mixture of two Gaussian, but it's already is a very fancy version, fancy description about data, right? Then you think about 3 Gaussian, 4 Gaussian, then you can actually have a very complicated distribution there, right? Do you agree? So, but now the question to say, can I recover these two underlying Gaussian model and decide which data should go to where? Because once I tell what are the Gaussian, underlying Gaussian component, then each data will have the way to assign to different distributions, right? Because we have this bear shape. For data close to your mean, basically your centroid here will have high likelihood, right? Because for people far away from you, it will have like the likelihood will drop very fast. But at the same time, once your data points move away from your centroid, it will drop the likelihood come from this Gaussian, but it quickly will pick up from the other component, right? The other components start to assign you a high likelihood. Then you obviously will convert to the other component. So in this way, I hope you start to see something very similar to k-means, right? Do you see that the link there? In k-means, you try to find a centroid and try to find who is my nearest centroid, right? Then I use a Euclidean distance as a measure. But here, you are trying to find what is a Gaussian. So once you are decided the Gaussian, then you know what is a mean, what is a variance. Yes. Yes, yes, exactly. That is that exactly what you need to infer. You need to decide what is a mean, what is a variance. Once you decide that, then you can start to fit data to the best, more likely the component. Yes. Exactly, yeah. So we will probably I will not cover everything, but exactly the same philosophy. So, but I hope, yeah, I think that you are absolutely in the right direction. But I hope first the people try to see the similarity to the k-means. I hope you will see we now change from a distance measure to a distribution fitting. You want to find who is more likely to which component, which distribution, which Gaussian component points are more likely to fit, right? So if you see this, I think the good for now. But then we have if you know there's, let's say, two model here, two cluster here. Okay, so you need to decide three things. What is the mean of each respective Gaussian? What is the variance of each respective Gaussian? And what weight you want to assign to each Gaussian? Okay, so once you decide these three, you are able to assign the likelihood. You are able to explain your data because your data, you know your data is come from a Gaussian mixture model. Okay, and then there's one constraint is that all the weights of the Gaussian need to be equal to 0 and the summation equal to 1. Why? Very simple, right? Because you need a distribution. You need to redistribute your Gaussian into multiple components. But you need the weight equal to 1 because you want to everything still add together into equal to 1 to be a density function, right? So I think that I just give two last sentence. So to do this is again, it's very similar to k-means. Is you start with guessing. You try to guess. You assign some numbers for mean, variance, and weight and the weights. Then you will try to, that is a so-called we call EM. You will have the E step. And then based on the E step, you will try to say, hey, under this assignment, can I recompute everything? Okay. Then you try to integrate. Once I recompute everything, then I can have another assignment. So basically, you will integrate between two steps, just like before. Okay, so we will come to details about this part. Yeah. Again, apologize for being late today. So good. Yeah, I will still see you on Wednesday. So I will say the good luck on Wednesday.